Welcome back to the Deep Dive. Our mission today is, well, it's pretty ambitious. We are going to move past the comfortable, everyday arithmetic you learned in high school.
We're going deep.
Deep. We're plunging right into the structural rules of abstract algebra. And this isn't just theory for the sake of theory. This is the bedrock. It's the foundation for, every secure transaction, every complex calculation that's running our digital world right now.
That's exactly right. You can think of this as a formal quest for what we might call perfect division. We've got a whole stack of concepts to get through, groups, swings, and fields.
Right.
And our goal is to really clarify a fundamental puzzle, one that's absolutely critical for systems like modern cryptography. The puzzle is this: why is division so unreliable in certain number systems?
And what is it about prime numbers that gives it this structural integrity, the thing that finally fixes the problem?
Precisely. We want to give you the insight into why, say, a composite number modulus guarantees a kind of computational failure, while a prime modulus guarantees success.
I really like that framing. The quest for perfect division. Okay, so let's unpack this. Where do we start? I think we should start with the most familiar concept in this whole domain, something we all use every day without even thinking about the math behind it.
Clock arithmetic.
Calculating with remainders.
Okay.
Okay, so let's start with an analogy that makes this tangible for anyone who's ever used a computer.
Which is everyone.
Exactly. So imagine a computer, but one with really limited storage. Like an old school machine that only uses, let's say, KL bits. It can only count up to a certain point.
Right, up to 2K to 1.
And once you try to calculate something larger than that, the system it wraps around. It essentially ignores all the high bits it can't store, and you're left with just the excess, the remainder.
And that, in a nutshell, is modular arithmetic. It is quite literally just calculating with what's left over, with remainders.
So how do we formalize this?
We use a concept, a theorem actually, called the division with remainder theorem. It's very straightforward. If you take any integer, let's call it $1, and you divide it by a natural number, which we'll call the modulus dollars, you get a unique quotient dollar and, crucially, a unique remainder.
That's fair. And the relationship is just a Q meter plus RRA.
Simple as that.
Now, that word unique is doing a lot of work there, isn't it?
Mm.
The uniqueness of the quotient and the remainder, that's a profound mathematical guarantee.
It is. It means that no matter how you perform the division, as long as you agree to constrain that remainder dollars to be between 0 and -1, we always land on the exact same spot.
There's no ambiguity.
Zero ambiguity. That uniqueness ensures consistency. And this leads us right into the formal language we need to use, which is the language of congruence.
Okay.
We say that an integer is congruent to another integer modulo. Now, most people, as you said, they learn this as a shortcut.
Right. The shortcut is just $80 leave the same remainder when you divide them by dollar.
And that's operationally correct. It's how you'd calculate it.
For sure. If it's, say, 3 p.m. on a 12-hour clock, and I ask you what time it'll be in 15 hours, you do the math. $3 plus 15, DT19.1.
And then you divide by 12?
You divide by 12, which gives you a remainder of 6. So 18 is congruent to 6, modulo 12. It'll be 6 p.m.
Exactly. But, and this is important, mathematicians insist on a more fundamental, a more rigorous definition.
Okay, what's the strict definition?
The strict definition is that $1 is congruent to $1. Diff and only if the difference between them. So bubble A is exactly divisible by $.
Okay, so it's not about the remainder itself, but about the difference being a perfect multiple of the modulus.
Yes.
Why? Why that insistence on the difference? What structural benefit does defining it that way give us that just, checking the remainder doesn't?
It's all about building proofs. It lets us prove things about the structure itself. For instance, say you want to prove that addition is compatible with congruence, that you can add two congruent numbers and the result stays congruent. It's far, far easier to prove that using the difference definition. If you know a dollars is a multiple of dollars, and you know a dollars is a multiple of dollars, then it's trivial to show that their sum is also a multiple of dollars.
I see. So the remainders might be messy, but the differences are clean multiples.
Exactly. It allows the formal structure to be built in this clean, elegant way that the remainder checking rule, while helpful for doing the actual math, doesn't immediately provide.
That's a great distinction, the engine room of the formal proof versus the tool you use for the actual operation.
Right. And this congruence relation is incredibly powerful. It brings us to a really foundational concept in set theory, which is the equivalence relation.
Right.
And that's where the magic really begins. This relationship of congruence, it is an equivalence relation. It satisfies 3 criteria: reflexivity, symmetry, and transitivity.
So why should we, or you listening, care about these formal labels.
Because this property, the fact that it's an equivalence relation, allows us to take the entire infinite set of integers, all of them, what we call math3bz, and neatly partition it. We can sort it into a finite number of distinct collections.
We're imposing order on infinity.
That's a great way to put it.
We're taking this vast, unruly number line and just organizing it, putting everything into small, manageable bins.
Think of it like a filing system, a perfect filing system. If we're calculating modulo 5, we have exactly 5 drawers. There's the 0 drawer, the 1 drawer, the 2, 3, and 4 drawers.
And these are what we call the rest classes, or residue classes.
Exactly. And every single integer that exists, 2 and 5, $100, $6 million dollars, every single one falls into exactly one of those 5 drawers, based purely on its remainder when you divide by 5.
So 25 goes in the 0 drawer modulo 5.
Yep. And $6 billion dollar lines goes into the 1 drawer.
So the integer theory was really just a representative. It's one member of its entire rest class. And the reason this is so incredibly useful for computation is that we've shrunk the problem.
Massive.
Instead of calculating with these potentially huge infinite numbers, we're now just calculating with a tiny finite set of remainders. That's why we call it a finite manageable system.
Precisely. We are exchanging the complexity of the infinite set math BBZ for the simplicity of the finite set of rest classes modulo dollar. And this structural move, this is the absolute first requirement for modern computation and for cryptography, where we need bounded, predictable results.
We've turned an unwieldy continuum into a small, predictable carousel.
A carousel, I like that, yes.
Okay, so now we have our finite bounded system. We have our carousel of remainders. Let's look at the operations. And the great news, right out of the gate, is that addition and multiplication are compatible. They play nicely with this congruence relationship.
They do, and this compatibility is the core source of all the efficiency we get from this system.
It means you can replace a huge number with its tiny congruent remainder, and the arithmetic still holds true.
Absolutely. If we know that Abel is incongruent to Abel and Abel is congruent to Baylor, then we are guaranteed, it's a mathematical certainty, that Abel plus Babel is congruent to Adel plus Badel, and just as importantly, Abel to Baylor is congruent to A, B, Babel, Bail.
Let's use that famous efficiency example to show just how powerful this is. Say you need to calculate 4110 modulo 7.
Okay, so calculating 4110 it's a huge number. I mean, even a modern calculator would start to struggle if that exponent were much larger.
But because we're in the world of modulo 7, we don't care about 41. We only care about its representative, its rest class.
So you take 41, you divide it by 7, that's 5 with a remainder of 6, so 41 tail Bail equivalent 7, 7.
And we can do even better, can't we?
We can, because 6 is just 1 less than 7. We can say that $6 equiv mandarin 1 paymod 7, 7. So we can substitute that huge number, 41, with just -1.
And just like that, the original problem, 41 paymod 7, 7, becomes 110 paymod 7, 7.
Which is just 1.
Trivial. We traded a massive exponentiation problem for a calculation you can do in your head. This substitution power is what makes modular arithmetic so foundational.
It is. We know that addition and subtraction are perfectly sound because of this. You can always simplify sums and differences, but, and this is a huge but, here is the structural warning. While addition and subtraction are secure, when we move to multiplication, the rules we take for granted from standard arithmetic, they start to crumble.
And the most dangerous collapse, the one that causes all the problems, involves cancellation.
Right. In standard arithmetic, if I tell you a c dot c equal b c dot c, and c dot isn't 0, you just...
Divide by c. You cancel it out and you get a b dot. We assume this always works.
We assume it because it does. But in the world of rest classes, cancellation is highly conditional. It frequently and catastrophically fails.
Let's look at a structural failure case. Let's use a composite modulus, say M6.
Okay, so our universe is now math BBC chi 6 2.
And consider the statement.
Yeah.
$4 equiv 2 times 3 and quit p mod 6.
All right, let's check it. On the left, $4 times 3 is 12. Since 12 is just $2 times 66, the remainder is 0 su. So $12 0 su CP mod 6.
Okay. And on the right?
On the right, $2 times 33 is 6. Since 6 is $1 times 6, the remainder is also 0. So $6 equiv 0, 636. The equation is $0 equiv 0 plus 6. That's mathematically correct.
The statement is true. But now, what happens if we try to cancel the common factor, the 3, from both sides?
If we do that, we're left with $4 equiv 2p mod 6.
Which is false.
Absolutely false. The difference is $4.22, and 2 is not divisible by 6. So the original equality held, but the attempt to divide or cancel that common factor led to a completely false conclusion.
This is the cancellation trap.
It is, and it happened because the number we tried to cancel, 3, and our modulus 6 share common factors. They are not coprime.
Let's do another one just to really drive home how dangerous this is. Let's use modulus 1 MPEL or $10.
Okay.
And the statement is $2.05 equal 4 times 5 P mod.
Left side, $2.05 equals $10. Modulo 10, that's 0 right side. $4.05, 220.10, that's also 0. So again, we have a true statement. $0 equiv 0.10 color.
But if we cancel the factor 5 from both sides,
we get $2 equiv 4 P-modity. And that is, again, false. The difference is 2, which is not divisible by 10.
and the failure is guaranteed, it's because the factor we canceled, 5, and the modulus, 10, share a common divisor. They both are divisible by 5.
So there has to be a rule. The ability to cancel isn't random, it's conditional. And the rule is very specific.
That's the rule.
You are only permitted to cancel a factor $3 if that factor equative is coprime to the modulus dollar.
Coprime, which is the standard term for the German Taylor-Fremd in the source.
Correct. It just means their greatest common divisor, the GCD, has to be 1. They share no common factors other than 1.
Coprimality is the green light for cancellation.
It's the safety check.
Okay, so let's demonstrate a successful cancellation. Let's use 188-osh. And our equation is $2 times 9 equiv 10 times 9 P mod 88.
All right, so here the factor we want to cancel is Sunan R9, and the modulus is 1/812. We check the GCD.
The greatest common divisor of 9 and 8 is 1.
They're coprime. We are safe to cancel a 9. If we do, we're left with $2 equiv 10 P mod 88.
And is that correct?
It is. The difference is $10 to 80 otters, and 8 is perfectly divisible by 8. Cancellation worked.
That is a profound structural difference. I mean, in our normal lives, we just assume multiplication can always be reversed by division.
Always.
But here, in this finite world, the ability to reverse, to undo a multiplication, depends entirely on whether the number we're using shares a factor with the size of our entire number system. If it does, the operation is just fundamentally broken.
Which is why we have to be so careful. And we have to remember we're working in this formal number space, the set of all our rest classes. And to ensure our mathematics is sound, we need one more guarantee.
It is.
Well-definedness.
Right. Well-definedness. This is the check that ensures the whole system is consistent. The operations are defined by picking any representative from a rest class, and the final result must be independent of which one we picked.
It's the proof that this whole concept of operating on classes instead of numbers is stable. Let's use our 1 in 6 example again. We know that the rest class 1 plus the rest class 0 should equal the rest class 1.
Okay, simple enough. Now let's pick two wildly different numbers that fall into those classes. For rest class 1, let's take 25, because $25, 4 times 6 plus a lumino.
Good. And for rest class 0, a multiple of 6. Let's use 666.
All right, so we add the representatives. $25 plus 691 by 6.
No, we just need to check which rest class 691 belongs to modulo 6. So we divide 691 by 6.
And you get a remainder of 1. The result is rest class 1.
So if we'd chosen the simplest representatives, 1 and 0, the result would have been 1. We chose 25 and 666, and the result is still 1. The final rest class is independent of our choice.
This consistency, this structural robustness, confirms that we can define addition and multiplication using these classes without worrying about the system breaking down internally.
We have built a consistent number space, but we are still plagued by this problem of unreliable division. And to solve that, we have to formally define the structural hierarchy we're operating in.
Okay, so we've established we have a number space where addition is always safe, but multiplication is risky, conditional. So to understand this divide, we need to zoom out a bit and look at the foundation of abstract algebra. And that starts with the most basic, fundamental structure, the group.
This is definition 1.2.13 from the source. A group is, at its core, just a set, let's call it 6. With a single operation, let's call it $, that has to satisfy 3 conditions.
And these 3 conditions are the absolute bare minimum for a reliable mathematical structure.
That's right. Condition 1 is associativity. This just means the way we group operations with parentheses doesn't matter. The sex star y4 is the same as 6a star dal.
Okay, that's straightforward. What's number 2?
Condition 2. It must have a neutral element. This is the identity element, which we can call Euler. If you combine any element $6 with Euler, you just get $6 back. For addition, this element is 0. For multiplication, it's 1. It's the element that does nothing.
And condition 3, this feels like the important one.
It's the core guarantee of the structure, the inverse element. Every single element 6 Eulers in the set must have an inverse, we call it 6-1, such that when you combine them 6 star x1, you get back to that neutral element.
And that's it. Those 3 things make a group.
That's it. And if the operation's also commutative, meaning the order doesn't matter, so 6 star y equals snar xe, then we give it a special name. It's an abelian group or a commutative group.
So why do we spend so much time focusing on this inverse element? It comes back to the cancellation trap, doesn't it? The ability to undo an operation is everything.
Everything. The mathematical truth, which is captured in a theorem, is that the cancellation rule only holds in a group because canceling an element in Nauer is fundamentally the same operation as multiplying by its inverse.
Oh, is it?
And if that inverse doesn't exist in your set, then you cannot perform the undo operation, and cancellation fails. The group structure guarantees that every operation can be uniquely and reliably reversed.
Okay, let's apply this framework to the numbers we know best, the set of all integers, to see where the structure holds and where it breaks.
Good idea. First, let's look at the integers under addition. The structure math BC plus, is it a group?
Well, let's check. It's associative. It has a neutral element, 0, Does every element have an inverse?
Yes. The inverse of any integer 6 lever is just Sapaspesi. And since Saxpel is also an integer, the inverse is guaranteed to be in the set.
So subtraction always works.
Always. Plus is a perfect abelian group.
Okay, now for the real test. What about the integers under multiplication? The structure times a crif. Is this a group?
Well, we have a neutral element, which is 1, but does every element have a multiplicative inverse that is also an integer?
No, absolutely not. Take the integer 2. Its inverse would have to satisfy the equation $2 times y example 1.
Which means $U has to be $12. But $12 is not an integer. It's not in our original set, Mac BBZ.
So the structure fails the inverse test. It is not a group under multiplication.
And that is a really powerful insight. The very act of dividing 1 by 2 forces you out of the system you started in. That's why dividing one integer by another often gives you a fraction, because the required inverse doesn't exist inside the set of integers.
And we see the exact same pattern in our rest classes.
We do.
Under addition, they are always groups. The inverse of a class 6 tolls is just the class Trackley, so subtraction is flawless. But under multiplication, they are not groups. Primarily because the rest class 0 never has an inverse. But as we saw, other elements might not either.
So we need a more complex structure, one that acknowledges this dual nature, perfect addition and subtraction, but conditional, often broken multiplication and division.
And that structure is called the ring.
The ring.
A ring is a set with 2 operations, plus and times, that have to interact in a specific, correct way. First, under the plus operation, the set must be a commutative group,
which guarantees reliable addition and subtraction. Correct. Second, the multiplication operation must be associative. And third, and this is crucial, the 2 operations have to be connected through the distributive laws.
So factoring out common terms, what the source calls ausklammered, that has to work correctly.
It has to. And if the multiplication is also commutative, if the order doesn't matter, we call it a commutative ring. And if it contains a multiplicative identity, the number 1, we call it a ring with 1.
Okay, so what's the status of our rest classes now? Where do they fit in this hierarchy?
And here is our second crucial status update for this deep dive. The set of rest classes, MathBZ, is always a commutative ring with 1 for any modulus dollars that's 2 or greater.
So addition, subtraction, multiplication, and distribution all function normally and consistently within this finite space.
They do. The ring structure is robust, but it still doesn't solve our core problem.
Division.
The fact that MathBZ is a ring doesn't tell us if every non-zero element has a multiplicative inverse. It only tells us that some might. We are still stuck in that conditional world.
We need to elevate the structure. We need to get to the gold standard, where division is guaranteed for everything. Except 0, of course.
And that higher standard, that pinnacle of algebraic structures, is the field.
Okay, the field. The source calls this the Kerper, or the King's class of structures. It's the ultimate algebraic structure for calculation.
It is, and it's defined as a ring where you can divide by everything except 0.
That is the critical distinction.
Formally, what it means to be a field is that the set of all non-zero elements must themselves form a multiplicative group.
In other words, every single non-zero element must possess a multiplicative inverse.
Every single one. Think about the numbers we use for, say, physics. The rational numbers, the real numbers, the complex numbers, these are all fields. In those structures, you never ever worry about division failing, as long as you're not dividing by zero.
So the question for us is, what value of our modulus dollar forces are finite worlds of rest classes to achieve this level of structural perfection?
And to answer that, we have to formally categorize all the elements inside the ring. We have to separate the good ones, the ones that work, from the bad ones that break everything.
The units versus the zero divisors.
Exactly. A unit is an element, a stellar, that is invertible. It's an element that possesses a multiplicative inverse, some other element, bigger dollars, such that their product, a Sibber ball, equals 1.
And the set of all these units in a ring is called the unit group. So if a ring is a field, that means every single non-zero element is necessarily a unit.
Correct.
Okay, let's go back to our broken composite ring, math BZ, to spot the units. Our modulus is $1. The non-zero elements are $1, $2, $3, $4, $5, $6, $7, $8, $9.
Right. We already saw that 3 is a unit.
Yes, because its inverse is 7. $3 times 7 equals 21.1, which is congruent to 1 modulo 10.
We also saw that 9 is a unit. Its inverse is itself, since 9 times 9 equals 81.1, which is also 1 modulo 10.
Okay, so 3, 7, and 9 are units. What about 4? Is 4 a unit in this system?
Well, we have to check. Can we find an integer dollar in our set such that $4 leaves a remainder of 1 when divided by 10?
Let's run through it. $4 times 1, $4 times 3, 0. $4 times 3 is 12 years, which is 2 mod 10.
$4, 4 times 14 equivs 6, 6. $4 times 5, 20, 20 equiv 0, 0. $4 times 6, 24 equiv of 1.
The pattern repeats. The results are just 4, 8, 2, 6, 0, and then back to 4. It never hits 1.
Never hits 1. Therefore, 4 is not a unit. It has no multiplicative inverse in the system.
So if 4 is not a unit, that means we cannot reliably divide by 4 in the ring. This brings us back to the most critical connection. How can we predict which elements are units without having to exhaustively check every single multiplication?
There's a key theorem that gives us the answer. A rest class, in the world of MathBZ, is a unit if and only if the representative r and the modulus dollar are coprime.
If and only if their greatest common divisor is 1.
That's the test. Text GCD at LM.
Okay, let's test that theory on our examples from MathEZ 10 For the number 3, the GCD of 3 and 10 is 1.
And it was a unit. Division by 3 is safe.
For the number 4, the GCD of 4 and 10 is 2. It's not 1.
And it was not a unit. Division by 4 fails. It's a perfect predictor. The units are precisely the elements that are coprime to the modulus, because that condition guarantees an inverse exists within the system.
Okay, so those are good guys. Now for the elements that cause all the structural failure, the zero divisors. They are the mathematical catastrophe waiting to happen inside a ring.
That's a good way to describe them. A non-zero element is formally defined as a zero divisor if you can find another non-zero element by dollar such that their product by dollar equals 0.
Which violates the most fundamental law of arithmetic we learn as kids. If two numbers multiply to 0, one of them must be 0.
Zero divisors break that law.
Let's go back to the modulus 1/6 centers. In that world, we know that the element 2 is not 0 and the element 3 is not 0.
Correct. But their product, $2 times 3, is 6. And $6 equivs 0 pi mod 6x.
So in the world of modulus 6, 2 and 3 are both zero divisors. They are the structural cracks in the system. They're what make multiplication behave so erratically.
And the presence of a zero divisor is devastating for solving equations. It's the reason cancellation fails. Think about it. If you have an equation 8a by x equal I say dot at y, you can only prove that 6y the equation well implies that 6y is equals somewhere.
But if it's e at dollars is a zero divisor,
then ax could be 0 even if 6y is not equal to a. A non-zero action can suddenly vanish into the zero class without either of the inputs being 0.
So we have established two kinds of non-zero elements inside these rest class rings. We have the units, which are coprime to dollars, and we have the zero divisors, which share a factor with the dollars.
And the structural landscape in MathBZ is beautifully, perfectly simple. Every single element that is not 0 is either a unit or a zero divisor.
It has to be one or the other.
It has to be. You cannot be both. Why? Because if an element shares a factor greater than $1 with the modulus dollars, then by definition its GCD with Ogata dollars is not 1, so it cannot be a unit. And because it shares that factor, it is a zero divisor.
This dichotomy is the mathematical firewall. And if we want our ring to become that coveted field, the structure of perfect division, then we have to eliminate every single zero divisor.
And that's it. The structural bridge is now complete. A rest class ring math BZ becomes a field if and only if it has n no zero divisors.
In formal algebraic terms, that's the definition of an integral domain. And in the special case of finite rings, being in an integral domain is the exact same thing as being a field.
It is. If you get rid of all the zero divisors, what non-zero elements are you left with?
Only the units.
Only the units. And if every non-zero element is a unit, then by definition, every non-zero element has an inverse, which means you've achieved guaranteed division. You've built a field.
So the task really just boils down to finding a modulus nuller that is so special, no number smaller than it shares a common divisor with it.
Exactly. And if nullars were a composite number, say 1 and 15, 5, then any of its own factors, like 3 and 5, would immediately become zero divisors. Because 3 times 5, which is $0, which is $0.
The moment you choose a composite modulus, you are guaranteed to introduce structural failure into your system.
It's baked in. And so we arrive at the core finding, the culmination of this entire deep dive. Math Ballers is a field if and only if my Ballers is a prime number.
And there it is. The moment where abstract algebra connects right back to the most fundamental concept in number theory.
It's a beautiful connection. Prime numbers are defined as having only two divisors, one and themselves. Therefore, if our modulus dollars is a prime number, let's call it Puller, then every single non-zero element between 1 and p of 1 must be coprime to Puller.
They can't share any factors because Puller doesn't have any factors to share.
So text to AE must equal 1, which means every single non-zero element is automatically a unit. No zero divisors. A perfect field.
Let's use a side-by-side comparison to really illustrate the consequences of this. Let's compare solving an algebraic equation in a broken system versus a perfect one.
Great idea. Let's start with the chaotic ring math BDZ. Our modulus is 6, which is composite. Let's try to solve the simple equation. $2x is 4p mod 6x.
Okay, the coefficient we want to divide by is AE22. And in this system, 2 is a zero divisor, since the GCD of 2 and 6 is 2, not 1.
So we should expect trouble. Let's test some values for 6,2. If we try 622, we get $2 times 2 equals 4, 3. That works. $4 equals 4p mod 6 double.
So 6 to 2 is the solution. What about, say, 6 to y?
Okay, $2 times 5 equals 10. And 10, when you divide by 6, leaves a remainder of 4. So $10 equals 4p mod 6 ducks. That also works.
So the equation has multiple solutions. That's already a problem for predictability.
It is. Now, what if we tried to solve a different equation in this broken system? What about $2 equals 1p mod 6x?
Well, let's think. $2 is always an even number. When you divide an even number by 6, what remainders can you get?
The only possibilities are 0, 2, or 4. It can never be odd, so it can never be 1.
The equation has no solution at all.
This is the structural chaos we're talking about. When you use a composite modulus, the resulting algebraic system is completely unreliable. An equation might have no solution, or it might have many, and that completely invalidates any system that relies on unique inversion, like cryptography.
You can't decrypt a message if the math gives you 3 possible answers, or none at all.
Exactly. Now let's compare this chaos to the perfect system, the field math BG. Here, our modulus is 5, a prime number. Let's solve the same kind of equation. $2 x is 4 per mod 5, 5.
Okay. In this prime system, our coefficient is 2. Is 2 a unit? We check the GCD of 2 and 5, it's 1.
So yes, 2 is a unit. It must have an inverse. We just need to find it. What number times 2 gives a remainder of 1 when divided by 5?
3. $2 times 3 is equal to 6, and $6 is equivalent p mod 5, 5. So the inverse of 2 is 3.
Perfect. And since we are in a field, we can reliably divide by 2. We do this by multiplying both sides of the equation by its inverse, 3.
So $3 equip 3 to it, 4 p mod 4 time, which is $6. Modulo 5, that's just high dollars. Or $6.
And on the right side, we have $3 4 times 4 apples except 2. Modulo 5, 12 is congruent to 2.
So the result is $6 equip 2 p mod 5, 5. A single unique solution. And the structural integrity of the field guarantees this. Every single non-zero linear equation, x Neville Bayes, will have exactly one answer, because the inverse of a dollar is guaranteed to exist and be unique.
This is the practical takeaway. This is the essential truth for anyone designing a secure computational system. The moment you choose a prime modulus, you eliminate all zero divisors.
Eliminating zero divisors means every non-zero element becomes a unit.
Every non-zero unit has an inverse.
And having a guaranteed unique inverse means you can solve equations uniquely, reliably, and consistently.
And this is why, to come full circle, this is why the reliability required for complex computation, and specifically the guarantee of unique decryption in cryptography, necessitates building those systems over prime fields, over math BZAT.
So when you're encoding a message with a key,
you must be able to ensure that there is only one mathematical inverse that can undo that encoding and reveal the original message. That absolute requirement for a unique inverse operation for guaranteed division is the entire reason why prime numbers are the foundational structural element of modern security mathematics. A non-prime modulus isn't just a bad choice, it's a security flaw baked right into the structure itself. Hashtag tag outro.
So we have successfully charted the hierarchy of these algebraic structures. We started with something as simple as a clock, we formalized it into rest classes, and then we discovered the limitations of the ring.
A structure where addition is always safe, but division is completely destroyed by the presence of these things called zero divisors.
And we saw that the difference between that structural chaos and what you called structural perfection comes down entirely to one thing.
Whether or not the modulus shares factors with the elements inside the system, if it does, you get zero divisors and structural collapse. If the modulus is prime, it shares no factors with any of its non-zero elements.